Hi everyone, I welcome you to the presentation of this lecture on loads with translational motion. So under loads with translational motion, you're going to have a motor connected to a load like this one. Then here we are translating, the motion here is not rotational motion, it is in a linear. As you can see, this rotational motion is translating that into a linear motion. Then from that side, that's when you're connecting the other load. So we have the following parameters. So the motor will have the torque, which is Tm, as well as the moment of inertia, which we are calling Jm. And that load, we are calling it load 1. It's going to have the torque, which we are calling TL1, or the torque for first load. And it will have its moment of inertia as well, which we are calling JL1. Okay, so for us to find the initial moment of inertia, is basically the summation of that for the motor and that for the load, which is connected before the translational mechanism there. Then on the other side, you've got that load. So the one which is connected, which is in translational motion here, instead of having the torque, we'll consider the force. And instead of having the moment of inertia, this time around it's a mass for translational motion. So we know that for loads with rotational motion, equivalent moment of inertia, it's basically the initial plus that for the load and the ratio, the gear ratio there. So this, when it converts to translational motion, it's basically that, because we know that J in rotational motion, in translational motion, is basically the mass, and the torque in rotational motion, it is basically the force. So here you have the equivalent moment of inertia. It's basically the initial moment of inertia, which will come from here, because this is before the translation. But after the translation, now it changes. So where there was J there, it's going to be a mass, and the turns ratio there. But this turns ratio is going to be a combination of the linear velocity as well as the rotational velocity. So it's the ratio of the linear over the rotation. So you're going to have a velocity there, which is in linear form. That's the one you put there. But on the primary there, the rotation you had there, the velocity you had was angular velocity, which is that one there. So our A will basically be defined by that. So as I said, torque in translation is basically the force. So from rotational motion, we have this equation. If you watched my previous lecture, I had explained. So when this one translates now, it becomes that. So the equivalent torque, it's basically the torque you're getting, which is here, plus the gear ratio, where there was torque there, this time around you have a force. That's the force you're having there, divided by the efficiency. So basically the equations are almost the same, except you need to know when you're in translational motion, take note of these. Where there is a moment of inertia, you have mass. Where there is torque, there is a force, like that. So with that said, let's solve this example. A motor has inertia, moment of inertia J is equal to 0.2 kg meter squared. It runs at a constant speed of 1420 revs per minute with a torque of 10 Newton meter, and drives a translational load which has a mass of 1000 kg to be lifted through uniform speed of 1.5 meter per second. It has a coupling efficiency of 8.5%. Determine number 1, the equivalent inertia referred to the motor shaft, as well as the power developed. So in our solutions, the equivalent inertia is basically this, which came from that. So from here you have all these parameters in the question there. So the initial is the 0.2 there, that's one we put. Mass we have is that one. Turns ratio, it's basically the linear velocity over the angular, but you need to convert this 1420, which is in revs per minute, it's supposed to be in radians per second. This is what you're seeing there. So you multiply that by 2 pi divided by 60. You're basically converting this into radians per second. Then when you do your math there, you're going to have that as your equivalent moment of inertia. Then for the equivalent torque, we have the formula, which is this one there. Just substitute the torque there, which was 10 Newton meter, it was given there. you have the mass for the force here. It hasn't been given, but we can calculate the force. We know that force is basically ma, mass times acceleration due to gravity. That's the one you're having there as your force. Then your gear ratio, which is this one, the one we had used there, and then multiply by the inverse of the efficiency, which is the one you're having there. On multiplying that, you're going to have that as your final answer. So this marks the end of my presentation on loads with translational motion. Thanks for watching.